We are going to talk about a particular type of continuous distribution called the normal distribution. And you may have heard of this before because it seems to crop up all the time. This is what the normal distribution looks like. This is its PDF. So we can see that the normal distribution has this, what we call a bell curve, and it means it's symmetric. It has one lump. Most of the values lie close to the center, and you get less and less likely to happen as you move away from that center. A normal distribution is parameterized by telling us where the centrality is and what spread it's got. What is its mean, mu, and what is its standard deviation, sigma. So we could have normal distributions with various different means. And what does that mean? We are shifting this big bell curve along the x-axis. And we could have normal distributions with different sigmas. And what does that mean? We are stretching or squeezing the bell curve together. If a random variable is normally distributed, then we tend to denote it like this. We say that the random variable x is distributed as, which is what that tilde thing is doing. It's distributed as, and then the normal distribution with mean mu and standard deviation sigma is denoted like this. A capital N with in order mu sigma in brackets. This seems to crop up all the time. If we look at the heights and weights of humans or any other animal, if we count how many people are on a bus in a day or whatever, the normal distribution seems to crop up all the time. It's a very, very popular distribution which seems to describe a lot of natural phenomena. And why is that? Well, one explanation comes from this. This is called a Galton board or a bean machine. And you can see that we have a load of ball bearings and they all start in the middle and they all have some sort of maze to travel through with gravity, and then they settle on an area, and the area they settle on shows the distribution of how many ball bearings settled in each area, and it seems to follow a normal distribution exactly. Why is this? Well, if we think about when you're starting your ball, dropping your ball bearing right in the middle, and its first obstacle it hits, it can go either of one way. It can either hit it and go to the left, or it can hit it and go to the right. And let's just say that that's 50-50. Then once you've gone to the left or the right, you hit another obstacle. And where are you going to go? You can either go to the left or to the right. And now you can start to see, well, what's going on here? We have that middle area. We have balls coming from two directions there, whereas the outer areas we only have balls coming from one direction. So there's going to be more built up in the middle area than in the tails. And we can carry on doing this again and again and again. And the more obstacles we have, the closer this is going to resemble a normal distribution, with most of the balls landing in the middle and not very many landing right at the end, and it being spread out like a bell curve. The reason it crops up again and again and again, the reason the normal distribution describes lots of natural phenomenon, is because of the central limit theorem. The central limit theorem is one of the most important results in probability and statistics. And it roughly states that if we have a load of random samples of n independent random variables and we sum them, the sum is a random variable that follows a normal distribution. This is really, really powerful because we are saying nothing here about the distribution of the component random variables that we are summing. We could sum things with an exponential distribution, or we could sum things with a discrete distribution or a bathtub distribution and so on. And eventually these will all sum, and the sum will follow a normal distribution. We can show this in Excel. Okay, I've opened up Excel and now I'm going to show you the central limit theorem in action. So in order to do this, each column here is going to be an exponential distribution. So let's show you one. I haven't showed you the formula for an exponential distribution, but I can sample it with this. So an exponential distribution with a parameter 0.2 going to be that multiplied by log of a random number. Sample lots and lots of these. Let's sample 1,000. Okay, so I've sampled 1,000 of those. To show you that this is exponentially distributed, let's draw a histogram of that. And we can see that the histogram here has that exponential distribution. Now, as a side note here, remember what I said about histograms in the video on plots. In Excel, Excel draws histograms and labels every bar the range. That is not a histogram. This should have a continuous range like a scatter plot. So if you do draw histograms in Excel, make sure you adjust that to get a proper histogram out. Okay, now let's duplicate this many times. Okay, so I've gone up to Z, so I should have 26 different exponential distributions. And let's just check that they all are. So let's just take a random column V and show the histogram again. And that's exponentially distributed. Now the column AA, that's going to be another random variable, which is the sum of all these random variables. So I'm going to sum the columns A to Z now. Let's do that for every observation. Now, what do you think the histogram of that column AA is going to be? The central limit theorem tells us that should be normally distributed. And we can see that that column AA, the sum of a load of exponential random variables, is normally distributed. It has that bell curve. And this will work for any sum of any random variables, whatever their distribution. And this is why the central limit theorem sort of crops up again and again. If you think about what my height is not exactly, but roughly the average of my parents' height. But they are the average of my grandparents' height. So I'm really the average of my grandparents' height. And so on and so on. What is the average? It's a sum of things divided by how many there are. So the sum of all my ancestors' heights divided by some scalar is my height. So my height would be normally distributed. Other things follow normal distribution for the same reasons. When I was first learning about this, I went and tried to find some data and tried to find something that was normally distributed. I took all the Oscar ceremonies that there were. I took the top 10 prizes every year, and I counted how many British people took home a prize. And I found that the number of British people taking home a prize follow that kind of bell curve. And why is that? Well, if you think about each person winning a prize is a random variable. They can either win the prize or not with a certain probability. And the probability is, how many British people there are in Hollywood, or how much Hollywood likes British people. Okay? And the number of people winning a Oscar that year is a sum of all the people winning prizes that year. It was a 1 if they were British and a 0 if they weren't. So I was summing those up to get the count of how many British people there were. So I was summing up a lot of random variables, and so that distribution was normally distributed. We know a lot of things about it. We know it is symmetric, and we can see that just by looking at it. What does that show? That means that the mean, the mu, is right in the middle of that distribution. The mean is equal to the median here. There is no skew. And because this only has one lump, we also say that that is the mode. Even though mode doesn't quite make sense for continuous data, in general we say the mode is where that lump is. And the mean and the median is in the same place as where that hump is. We also know things about its spread. we know that 65% of all values lie within one standard deviation of the mean. So 65% of the values have a distance at least one standard deviation away from the mean. We can go further. We know that 95% of values lie within two standard deviations of the mean. And 99.7% of values lie within three standard deviations from the mean. And look, we can see that bell curve happening now. Most of the values lie close to the mean, and the further away we go, we're adding less and less values every time. So our tails get thinner and thinner.